It's important to know the impact of even a single sample delay. It's surprising how much a delay of a 44,100th of a second can make on your signal. And it turns out that around us, all over the place, we're dealing with these short delays. And we're dealing with the phase cancellation that is imposed with those delays. So in this next video, we're going to look at the impact of taking a very short delay and what happens when we get longer and longer delays. We'll start with just simple white noise, which is equal noise, which is equal amplitude across the frequency spectrum. And we'll add slight delays mixed back with itself, and we'll see how the spectrum changes based on that. At first, it'll look like just a deep notch in the frequency spectrum, and eventually we'll get a series of related notches that are harmonically related, which we know as comb filtering, and then eventually we get to the point where we hear a delay. When we get to that point, we'll switch to using more percussive sounds and just explore as we increase that delay kind of what it sounds like. And I just want you, as we're doing this, to kind of relate it back to what you hear in nature. Because delays are around us all over the place. And just like the dynamic effects that you have to kind of learn to hear them and learn to recognize them, you want to start to learn and recognize the sound of delay effects. And this idea of comb filtering is a really important one because it's always giving us trouble when we are recording. Remember, a delay is a reflection off a surface. And every time you put a microphone in front of an object, you have to be careful of other surfaces around you. Because the sound from that object, well, the sound from that source will bounce off all these other objects and hit that microphone as well. So when we look at delay effects, it's also related to what happens when we record. And these kind of deep notches plague us in recording. We call it phase cancellation and comb filtering. So we have to be very careful with that. So in this next video, we're going to look at the spectrum of delay, what happens as we increase delay time, and I'd like you just to remember to relate that back to what you hear in the real world all around you.
We'll start our examination of the delay spectrum with the shortest possible delay, a single sample. I'm going to demonstrate this by taking two audio files, which are the exact same audio file in both white noise, and white noise is equal energy across the frequency range. So these two audio files, which are exactly the same, are being placed on two separate tracks and are being added together here before they're sent to the displays you see in front of you. I'm then going to delay one of those two copies by a single sample, and we're going to see how big an impact that has on the overall spectrum. And then we'll try to use longer and longer delays from there. So here is white noise. Again, this is two of the same exact white noise audio files played together, and then I'll be delaying one of the copies by a tiny increment. So there is white noise. You see equal energy across the frequency range. Now I'm going to delay one of the copies. So that was a single sample of delay. And you can see right here in the sonogram how we have a major cut in the high end with a single sample delay. Let me try two samples. Two samples of delay gives us a serious notch, right around 12K. That's two samples. That's 2/48,000ths of a second. It's amazing how a small delay can have such an impact. Let's try more. That's three samples, 4, 5, 6, 7. That's 48 samples of delay. And we start really seeing the idea of a comb filter. And a comb filter is called that because it has this series of notches. Now it's very important that you start being able to hear the sound of comb filtering because it's all around you. Let me go a little further. This demonstration shows us clearly the impact of combining a sound with a delayed copy of itself. And this happens when you're recording. Imagine I'm recording an instrument and I have a microphone in front of that instrument. The sound goes from the instrument, arrives at the microphone. But the sound also bounces off a nearby flat surface and arrives at the microphone a little bit later. That is combining a sound with a delayed copy of itself, just like we've done here. And there is definite possibility you will get comb filtering in your recordings if you have this situation. So this is why we need to be so careful about any nearby flat surfaces when recording, because we will get comb filtering, and it's probably going to have a negative impact on our sound. Now that we want to move to longer and longer delay times, it's going to be useful to switch to a percussive sound so we can hear that transient and we can note when that transient becomes doubled and when it sounds like two separate hits. Again, we're taking the same exact sound and just delaying one of them. Here we go. Here's a snare sound with no delay. I'm going to slowly bring up the delay time. Now we're at a 1 millisecond delay. 2 milliseconds, 3 milliseconds, 4 milliseconds, 5 milliseconds. So over that entire range, up to 5 milliseconds, we've been hearing that shifting comb filtering sound. I'm going to now continue to raise the delay time up even further. 6 milliseconds, 7 milliseconds, 9, 10 milliseconds. It's starting to sound buzzy, and I'm almost noticing a pitch in there somehow. Let's continue on. 18 milliseconds, and it feels a little bit like a flam. And by the time I'm at 36 milliseconds here, it really feels like I have two different hits. I notice the delay as two separate events. In this final exploration of the delay spectrum, we're going to take a different approach. This time, I'll start with a very simple, clicky sound. Let's hear it. I'm going to run that sound through a simple delay, and I'm going to have the feedback all the way up. And we're going to see that very short delay times actually create a pitch. In fact, throughout this entire week, we're going to be exploring the curious relationship between delay and frequency. So let's try this out and see what happens. We'll start with our sound. It's kind of clicky and it's repeating. Now I'm going to engage the delay. It's 100% wet, feedback is all the way down, and my delay time is 1 millisecond. I'm now going to increase the feedback. As we increase the feedback, a pitch will emerge. Because our sense of frequency is our perception of things repeating very fast. And what we've done with this delay is created very quick repetitions, so fast that we perceive it as a pitch. I'm now going to increase the delay time. Right now it's on 1 millisecond, and I'll increase it. 1.1 milliseconds. Eventually, we get to the point where we start hearing it as separate attacks, as we hear it as a rhythm. This kind of exploration, it probes the edges of our perception. At what point does the delay become pitch? How is delay and frequency intertwined? What are the edges of human perception, and how can that be explored musically? These kind of interactions between delay and frequency and delay and filtering are explored heavily throughout audio effects. We're going to find these characteristics show up in our chorus phasers, flangers, short delays, long delays, and reverbs, and our filters. It's an incredibly important spectrum, this delay spectrum. And honestly, it's kind of difficult to kind of wrap the brain around. How are all these interactions really working, and how can we use them musically?